we would look at one more problem involving Navier-Stokes equation, and this would probably be the last problem to deal with in this specific part of the course, and we would move on to something different. However, I would supply you with a list of a number of problems with answers which you can try on your own, and if there are any questions, I will be glad to answer those queries. So far what we have done, what we have seen is that the velocity, we were dealing with only with 1D velocity, that is, the velocity is a function of it's a one-dimensional velocity case. But there can be situations, many of the situations that are common to our everyday experience, the velocity can vary with in more than one dimensions. It could be a function of x and y, r and theta, and so on. So in those cases, you would see that it is still better to start with Navier-Stokes equation. It's impossible to use the shell momentum balance in such cases. So you start with Navier-Stokes equation and you get the governing equation and identify what would be the boundary conditions. In some of the cases, it is possible to use certain simplifying assumptions. So those assumptions must be mentioned clearly in order to obtain a closed form solution for velocity. And these assumptions are sometimes can be used as the asymptotic solution of the governing equation under certain special conditions, which would tell us something about the physics of the process, and it could be extremely helpful in many such situations. So what we are going to do, the last problem in this series, we are going to look at the flow between two parallel plates, where the fluid enters through one of the plates at the center and then distributes itself at in the intervening space between the two discs. So we have two discs, circular discs, one on top of the other with a certain separation in between, and through the top disc at the center, through a hole, the liquid enters the space in between the two discs, and then they start radially flowing in the direction the way my fingers are pointing. So it's a radially outward flow in between two discs once they enter from the top at the center. So and there is a pressure gradient, and since that these two discs are horizontal, there is no effective body force to speak about. It's only the pressure gradient which drives the fluid radially outward. And it is also clear that the no slip conditions on the top plate and on the bottom plate must be adhered to. So therefore the velocity is going to be 0 at this point and 0 on the bottom plate as well. So the principal motion, as it's clear from the figure that I have drawn over here. So we are looking at the radial flow between two parallel discs, and the two discs that I have drawn, they have the top one has a hole at the center, and then in between the two discs the fluid starts to move outside. So it's definitely a cylindrical coordinate system. But in this cylindrical coordinate system, there can be three components of velocity: Vr, which is in the radial direction, V theta, which is in the theta direction, or Vz. So if you look carefully for at the space in between the two discs, it's the only Vr, the velocity in the radial direction, which exists. All other components of velocity, namely Vz and V theta, are 0. However, there is an assumption involved in this. Think about the hole at the top plate. The liquid enters through that hole, comes the space in between the two, changes its direction, and then starts to flow radially outward. So there is a region very close to the inlet where the flow changes its direction, where the flow can be a function of function of z as well, where it could be a function of r, and so on. So we, in our analysis, we are not taking into account the region which is very close to the inlet. So all our analysis is valid from this point, that means from the hole to the outside of the disc, and not right under the hole, where the flow situation is extremely complex. So now you see that in the space between the two discs, you only have velocity in the r direction. Now this velocity in the r direction is a function of z, where you are with respect to each of these plates, and as the fluid moves outward, the area available for flow keeps on increasing, because the area available for flow is simply twice pi small r times h, if h is the distance between the two discs. So as the flow goes to a higher and higher radius, the flow area keeps on, the flow area which is perpendicular to the flow direction, which is twice pi r times h, that also keeps on increasing. So as the flow area increases, the velocity must decrease in order to satisfy equation of continuity. So Vr is not only a function of z, it's also a function of r. This has to be kept in mind. So we are dealing with a velocity which is a function of r, and as well which is a function of z. Whenever we come across such a problem, we first try to see if use of equation of continuity can somehow simplify the situation. So that's what we are going to do first. We're going to use the equation of continuity in this and try to see if a simplification is possible. So as I said, the top disc and the bottom disc with a separation of twice b in between them, and the flow comes in through a hole whose radius is equal to r1. The radii of both the discs, they are equal to r2, and the flow is moving radially outward. So as the flow comes towards the outer edge, the cross sectional area increases, so the velocity reduces, and we are not going to deal with the region below r1, because we understand that the flow situation over there is extremely complicated. So as I said, the first thing to do is to use the equation of continuity, and from the equation of continuity try to see if any compact formation is possible. So the r component of equation of continuity in cylindrical coordinate systems would simply be rho r Vr, where Vr is the r component of velocity, and since v theta and Vz are 0, this is the only non-zero term in the equation, and therefore Vr would be some phi by r. Now we realize that velocity in the r direction, as we have as I have mentioned before, is going to be a function of z and r. Now since d dr of r Vr is a constant, or rather d dr of phi is equal to 0, then from this relation it is clear that phi is a function of z. Once again, d dr of r Vr is 0, so if I bring r on this side, d dr of r Vr is equal to d dr of phi, which is equal to 0. So phi is not a function of r. However, since Vr is a function of z and r, phi has to be a function of z. So from this relation we understand that phi cannot be a function of r, but since Vr is a function of z and r, so phi has to be a function of z. So that's the first thing that we can obtain, and we have an approximate we have an expression for Vr just by looking at the equation of continuity, where the only thing that we need to do is try to see how can we evaluate phi. Now, which component of Navier-Stokes equation that we are going to do next? Now, it's a cylindrical coordinate system. V theta is 0, Vz is 0. So, we must start with the r component of Navier-Stokes equation in cylindrical coordinate system that will describe the flow in between two parallel disks when they are separated by a distance twice b, and when there is a pressure gradient forcing the liquid to move radially outward. So, we start with the r component of the Navier-Stokes equation. So, I will write the r component, which would be so this is the entire left hand side. So, you can again identify that this is the spatial term, and all these 4 terms, since they have velocity explicitly present in them, they refer to the convective transport of momentum. So, these are the convective transport of momentum. This is the pressure gradient in the r direction. What you have are the viscous transport of momentum, 1, 2, 3, 4 terms, and then you have a body force term. So, as before, we are going to see which of these terms can be neglected. First of all, it is a steady state. So, this is equal to 0. Vr does not vary with t. Coming to the end, I would also write this the continuity equation just for our reference, which was 1 by r this was the equation of continuity, which we have seen in the past this thing. So, here Vr is not 0 and del Vr del r is also not 0. So, as the liquid moves towards larger and larger values of r, the Vr has to reduce. So, Vr slows down with r, therefore, we cannot say anything about, we cannot equate this term to be 0. So, this will remain in the governing equation. Here we have this term, the V theta would be 0, and in this case V theta would be 0 once again, and even though Vr varies with Z, however Vz is 0. So, therefore, of the entire left hand side, the only term which remains is rho times Vr del r. There is a fixed pressure gradient present in the system. So, I must keep del P del r in here. I will come to this at a later point. If I think of this term, Vr is not a function of theta. So, therefore, this is going to be 0. There is no V theta present in the system. So, this term would also be 0. However, del square Vr is a function of Z. So, I cannot neglect, I cannot make this term, equate this term to 0. So, this will also remain in the governing equation. And since the disks are horizontal, so there is no body force acting on it. So, therefore, this will also be 0. So, of all the terms on the right hand side, this is non-zero, which will remain in the governing equation. This is non-zero, everything else is 0, and now we come back to this term. Now if you remember from what we have obtained from the continuity equation, is that Vr is equal to phi by r, and we also realize that it's a function of z only. So if it's a function of z only, so this is simply del r of rvr, and del r of rvr is simply phi. So I have phi, I can replace this with phi, and since phi is a function of z only, the differentiation of phi with respect to r must therefore be equal to 0, which would allow me to cancel this term as well. Once again, this rvr is equal to phi, and we have realized from our previous discussion that phi is a function of z only, phi is not a function of r. So if phi is not a function of r, therefore del r of phi would be 0. So therefore this term is going to be equal to 0. So my governing equation would consist on the left hand side as this term, on the right hand side this one, and this term. So the governing equation would simply be equal to minus rho Vr del Vr by del r equals minus del P by del r plus mu times del square Vr by del z square. So this is the governing equation for flow in such a system, and I am going to substitute Vr and del Vr del r from this relation. So what I would get is minus rho phi by r into del Vr by del r, which would be minus 1 by, sorry, this is plus, this is not minus, this is not minus, this is plus, 1 by r square in 1 by r square. So del Vr del r, if you see del Vr del r, it would be 1 by r square into phi is equal to minus del P del r plus mu times del square Vr by del z square. So final form of this would be minus rho phi square by r cube equals minus dp dr. I am consciously using dp instead of del P because P is a function of only r. It does not vary significantly with z or with theta. So your this thing would be and if I substituted this in here, my governing equation would simply be so substituting Vr in here, you would obtain d2 phi by dz square, and since phi is a function of z only, so I can drop the partial sign, it would simply be d2 phi by dz square, and the r over here would simply come at this point. So my reduced form of the governing equation for flow between two circular disks as a function of applied pressure gradient would simply take this form. So again you see the utility of Navier-Stokes equation, how easy it is to at least arrive at the governing equation. There is no need to think of any complicated shell, which would be very, very complicated in this case. You simply pick the form of pick the direction in which the velocity varies and try to solve it. So this is your governing equation. The problem with this specific equation, that it's nonlinear. It's a nonlinear equation. The nonlinearity comes because of the presence of this term on the left hand side. Since this presence of this term makes it nonlinear, the solution, there is no way to obtain an analytic solution for this case. But if we try to think about the genesis of this nonlinearity, then probably it would give us some idea of some asymptotic condition in which this nonlinear term, the effect of this nonlinear term would not be significant. So, if you again look at the derivation, you would see that the nonlinear term arises from the left hand side of the Navier-Stokes equation, and the left hand side of the Navier-Stokes equation, as I said many times before, is due to the convective transport of momentum. Now, what is convective transport? What is the root cause of convective transport of momentum? It's because you have a flow, and with the flow carries some momentum along with it, which is nothing but the convective momentum. Now, if there are situations in which you can say that the effect of this convective momentum is rather small, then you would be able to drop the nonlinear term on the left hand side. Now, since it's related to velocity, since this nonlinear term is related to velocity, the only way when you can drop this term, or when you can disregard the contribution of this term into the overall scheme of things, is only when the flow is very slow. So, if the flow is slow, the convective transport of momentum can be neglected, but not the conductive transport or the molecular transport or viscous transport of momentum, because unlike convective transport of momentum, the viscous transport of momentum does not depend on velocity, rather it depends on velocity gradient. So, keeping the velocity low, assuming that it's a low velocity situation, will let you drop the convective term, but will not necessarily you are in a position to cancel the viscous terms. Okay. So, if the contribution of the term, mathematically speaking, is truly zero, then those special flow conditions in which the convective term, the effect of the convective term can be completely neglected, are known as the creeping flow situation. So, the case where this entire term is equal to 0, they are called the creeping flow. Okay. So, this creeping flow condition, which are, as the name suggests, it's a very slow flow. So, the convective transport is small, but the viscous transport may not be small. So, when this term is equal to 0, that is known as the creeping flow condition. So, the analysis that we are going to do from this point onwards is only valid for creeping flow or close to creeping flow solution where the nonlinear term can be dropped. So, my governing equation then becomes only this is equal to 0. Since the left hand side I have made it equal to 0 by assuming it's a close to creeping flow situation. So, what I have then is mu by r times d2 phi by dr square is equal to dp by dr. So, this is creeping flow. This can now be integrated. Phi is not a dz square. Phi is not a function of r. So, I can keep it outside the integration sign. This is dr by r from r1 to r2, and this is dp. Let us say the pressure at the two locations are P2 and P1, and therefore, you can write ln r2 by r1 upon integration times d2 phi by dz square would be equal to P2 minus P1. So, if we define delta P is equal to P1 minus P2, then the equation would transform to R2 by R1 d2 phi by dz square plus delta p is equal to 0. So this is now a straightforward equation, second order equation in terms of phi. So creeping flow lets me simplify the equation, governing equation, considerably to obtain a compact expression where phi is a function of z, its phi is not a function of r, pressure is a function of r. So therefore I perform the integration and I obtain this expression for the for phi. So what I do next is I find out what is d phi dz, which would be minus delta p z by mu times ln r2 by r1 plus c1, and finally phi to be equal to minus delta p z square by 2 mu ln r2 by r1 plus c1z plus c2, where c1 and c2 are constants of integration. So if c1 and c2 are constants of integration, and then they should be evaluated using appropriate boundary conditions. See, what the way we are trying to handle this problem is, we understand that Vr is simply going to be equal to phi by r. Phi is a function of z only, it's not a function of r. So our aim is to obtain an expression for phi. The expression for phi can be obtained if we write the r component of Navier-Stokes equation in cylindrical coordinate systems. That's what we have written. But we have seen that unlike in previous cases, there is a contribution from convective momentum. There is a contribution from the left hand side of Navier-Stokes equation. On the right hand side, the terms which would remain are the pressure gradient and the variation of velocity Vr with z. Okay. The other terms can be cancelled based on our understanding and based on the use of the continuity equation. The first term inside the third bracket, the first viscous term, can be cancelled because of the use of the continuity equation. So there will be three terms in the equation. One is the convective transport of momentum, one is a pressure gradient, and the other is a viscous transport, mu times del square Vr by del z square. The presence of the convective term makes the equation non-linear. We have to get rid of it if we would like to find an analytic solution. So fundamentally we understand that this contribution, the convective contribution, comes from velocity in the r direction and the change in the surface area in the r direction. So we have a convective contribution. When this convective contribution can be neglected, will be small when the velocity itself is small. So velocity small will let me allow as a special case in the limit when the convective term can be completely ignored. Mathematically that is known as the creeping flow case. So the convective term, the nonlinear term, is neglected since we are dealing with a very low values of Vr, but that does not mean the viscous transport can be neglected, because it depends on the gradient and not on the value of the velocity itself. So if we use the creeping flow, then we have only two terms present in it. One is a pressure gradient term and one is the variation of velocity with respect to z, that term. We already have an expression for Vr, which is, if you look again, which is phi by r. So somehow I have to obtain an expression for phi. So I put that expression into the governing equation, and what I obtain is an expression of phi only. This equation can now be, so this equation can, this is the equation which can now be integrated, and this is the final form of phi, where C1 and C2 are two constants of integration which will have to be evaluated. Phi, which is minus del p z square by 2 mu ln r2 by r1 plus C1z plus C2, this would give me VR, which I realize is a function of R and Z. Phi is a function of Z only, but VR is a function of R and Z, as we have seen from our equation of continuity is phi by R. So this would be minus delta P by 2 mu R ln R2 by R1 times Z square plus C1 by R Z plus C2 by R. So see how we have got the expression for VR from the expression for phi, identifying it's a function of Z, and this is from equation of continuity, the specific form of VR. What are the boundary conditions? The boundary conditions are essentially no slip at the top plate, at top and bottom plate. In other words, mathematically, VR, which is a function of R and Z, would be 0 at Z equals plus B and at Z equals minus B at the top plate and at the bottom plate. However, we must realize that it's valid in a region where R is greater than R1 but less than R2, where R1 is the radius of the hole at the top through which the liquid comes in to the space between the two discs, and R2 is the radius of the two discs, outer radius of the two discs. So the domain of applicability of these two equations, of this equation is only between R1 to R2. So that's what it simply means, that it's going to be between R1 and R2. So with these two boundary conditions, one should be able to evaluate what is C1, which would turn out to be equal to 0, and the expression for C2 would be equal to delta P B square by twice mu ln R2 by R1. So your VR, which is a function of R and Z, with this expressions for C1 and C2 would finally come to be delta P B square 2 mu R ln R2 by R1 1 minus Z by B whole square. So this is the final form of the velocity expression for the case of pressure gradient driven flow between two parallel plates which are separated by a distance twice b, where the geometric parameters are R1 is the radius of the hole through which the liquid comes in, R2 is the outer radius of both the plates, delta P is the applied pressure gradient, and mu is the viscosity of the liquid in between. If we have, since we have the value of VR, it is then easy to calculate what would be the value of Q, because most of the times we are not interested in finding out what is the velocity at every point in the flow field. We are more comfortable in dealing with the average values. For example, the average velocity, or from the average velocity one can obtain what is the flow rate. So the flow rate would simply be twice pi minus b to plus b r VR dz. So this is area averaged volumetric flow rate, where the dz can vary from minus b to plus b, and what you have, and RVR is simply equal to phi from our equation of continuity, and we understand that phi is a function only of z. So this is consistent, this expression of Q is consistent with our understanding, and it follows the physics of the problem. So Q would simply be equals twice pi delta P, after you put the expression of phi in there, B square pi 2 mu ln R2 by R1 from a minus B to plus B 1 minus Z by B whole square and dz. And after one or two more steps, then R2 by R1. So here you see how it is how we get a compact expression for the flow of a liquid, a Newtonian liquid, in between two plates in laminar flow when there is a pressure gradient and when there is no effect of gravity. But the major assumption that we have incorporated put in here is that the flow is very slow. That means the flow is can be termed as creeping flow. What is the speciality of creeping flow? There is no contribution from the convective transport. The only contribution to momentum transfer is due to the viscous transport or the pressure gradient and body force if it is present. But momentum transport due to convection is absent in the case of creeping flow. So a nonlinear equation which we have quickly obtained from our analysis of the Navier-Stokes equation has led to a complicated expression which, with the use of the right approximation assumption, has given rise to an expression, a governing equation that can be integrated, that to obtain the value of phi, where phi is the z component dependent, the z direction dependence of velocity, and we can obtain the point value, the expression for velocity, the expression for average velocity, and the expression for the volumetric flow rate, as we have done here. So this is another nice example of the use of Navier-Stokes equation to solve problems like this. There can be many other problems, more complicated problems of Navier-Stokes equation, some of which I would try to give as an exercise problems to you, and there would be more complicated problems which are beyond the scope of this specific course. So, but whatever it is, I would like to summarize so far what you have understood. What I tried to convey to you is that shell momentum balance is, for beginners, it's a good thing because it gives you some handle on the concepts involved. But the moment you deal with slightly complicated problems, you feel the need for a more generalized approach, which is provided by Navier-Stokes equation. And I think I have solved 5 or 6 problems in this part of the course to give you some idea of how to handle such situations. And we would solve few more problems in our tutorial part. So I think I will end here, and this would be the like conclusion of our part of Navier-Stokes equation. And what I am going to do from next class onwards is try to introduce the concept of boundary layers, which the concept of boundary layer is extremely important in transport phenomena, and I would give you an overview of the boundary layer, how it can be solved, how they are connected with many of the problems that we encounter in everyday life, and I would try to give you examples to which you can relate to. And this would give us some idea about what is the effect of boundary layer, the utility of boundary layer, how you can modulate the boundary layer to get more transport. And you would see that most of the transport is confined near the interface, near the solid liquid, the solid fluid interface. So if we can manage that, understand the physics of that, then we are in a very good position to alter the boundary layer and to get the desired transport from a specific system. So that's what we are going to start in the next class. Thank you.